In this lesson, we're going to dive into the world of Einstein and talk about one of his theories that he's famous for, and that's the theory of special relativity. Specifically, we're going to talk about a phenomenon he discovered called time dilation. Now, to set the stage here, we've been talking recently about relative velocity, how the concept of velocity doesn't make sense unless you have an object to compare the moving object to. So I often like to say, if there was only one object in the universe, there would be no such thing as motion for that object. Not just that we wouldn't be able to tell if it was moving or not, but the concept of motion would not exist. Motion, in order to have motion, you need to have something to move relative to. If we had a universe with two objects in it, and they were doing different things, they were going past each other, then motion would be possible. So the idea of motion is only possible relative to another object. That's why we've spent a fair bit of time up till now talking about motion, where we not only name the object that's moving, but the object that we're measuring that motion from, the object that it's moving relative to. We did a lot of problems where there's a boat moving relative to the river, and both of those are moving relative to the ground. So we're going to kind of use some of those same ideas, but kick things up a notch. Instead of a river flowing over top of the ground and having a boat moving on top of it, we're going to have a train moving over top of the ground. And inside the train, we're going to have a laser. And what makes a laser better than a boat? Why do we need a laser in this lesson? And why isn't a boat good enough? Lasers can move really, really fast. Or rather, the light from a laser moves really, really fast. Much faster than a boat could. So, to set the stage for Einstein, let's talk about some people who came before him. We'll start with Newton. And Newton figured out something very important. Newton figured out that it's impossible to tell if something is moving. There's no, when I say this, people might kind of take offense at first and say, well, yeah, it's possible to tell if something's moving. For example, my car has a speedometer. That tells me not just if I'm moving, but how fast I'm moving. Isn't that proof that we can tell how fast something's moving? Well, I guess my response to that would be, okay, so if you park your car in the driveway, speedometer says 0, that should mean the car is not moving. But your car is on planet Earth, and planet Earth is rotating pretty fast, and it's revolving around the sun. It's on this path through space. That's even faster. So that speedometer isn't necessarily actually telling you if you're moving or not, because it hasn't registered that specific motion. Your speedometer can tell you if you're moving relative to the ground, but it can't say whether you're moving without referencing that other object. And so you might think, well, okay, let's design something more fancy than a speedometer. You know, we have GPS and on all those sorts of things. But a GPS only tells, what your motion is like relative to the satellites that are measuring it. So there is no way to say definitively an object is moving or an object is not moving, because motion only exists, like I said, relative to other objects. You can have a situation where an object might have more than one speed. Maybe a car is driving down the highway in the fast lane at 100 kilometers an hour, and it drives past two people. One of them is a pedestrian on the side of the road sitting there. They'll see the car go by them at 100 kilometers an hour. One of them is another driver. This one in the slow lane may be going 80 kilometers an hour. that driver would see the first driver go past them at 20 kilometers an hour. So you've got the pedestrian looking at this fast car saying it's going 100. You've got the other driver in the slow lane looking at the fast car saying it's going 20. So what's the car's speed? Well, both of those speeds are correct. The car is going 100 relative to the pedestrian, and it is going 20 relative to the other car. So the concept of motion only makes sense relative to other objects. That's why, like I said before, in a universe where there was only one object just floating around in space by itself, the concept of motion couldn't even exist. A fancy way of saying this, or a simpler way of saying this, is that motion is relative. So if there's no experiment I can possibly do that tells me if I'm moving or not, because there's no such thing as moving or not, unless I compare myself to another object, then that means the laws of science must be the same for me regardless of my motion. If the laws of science were like different if I was moving than if I wasn't moving, then that means I could do something that might have different results if I was moving than if I wasn't moving, because it would have to obey different laws. And if I could get different results if I was moving than if I was not moving, then I could use that experiment to determine if I'm moving or not. But we already said that's not possible. So what we say is that the laws of science are the same for all inertial reference frames. I'm going to break this word down a little bit. A reference frame is just a place where you can view something from. In our sort of unit on relative velocity, the two places we often viewed the boat from were the river and the ground. So the river was a reference frame and the ground was a reference frame. So a reference frame is just a fancy word for a perspective. Now the word inertial comes from the word inertia, and inertia is resistance to acceleration. So an inertial reference frame is a reference frame that is not accelerating. In other words, it has constant velocity. So, as long as I'm in an inertial reference frame, meaning as long as I'm moving at constant velocity, it doesn't matter what my motion is, the laws of science must be the same. So no matter what experiment I do, regardless of my motion, I will always get the same result, as long as that motion is at constant velocity. An example I like to use to drive this point home is here. Imagining two scenarios. One where I am inside a train and I drop a ball. And this train, we'll say it's made of glass, it has big glass windows so people from the outside can look in and see what's going on. This train is stationary relative to the ground. It's just sitting there on the track. There's another scenario where, say a little while later, that train starts to move. And it has a velocity moving down the tracks with a speed v. My original train over here has v equals 0. It's not moving. So in both of these situations, I perform an experiment. I take this ball here and I drop it to the floor. And then when the train's moving, I take the ball and I drop it to the floor. Because the laws of science, because both of these trains are inertial reference frames, they both have constant velocity, then the laws of science are the same in both trains. That means My ball should obey the same rules, and I should kind of get the same results in both of these situations. And indeed, if you were to do this experiment, regardless of whether the train is moving or not, you would find the ball lands in the exact same place, probably right beside your toe, and you'd find that it takes the exact same amount of time for the ball to hit the ground. Now, that's an example of a pretty simple experiment, dropping a ball, seeing where it lands, and timing it. But you could devise a much more complicated experiment, as complicated as you want, and you'd still get the exact same results in both of these situations. The situation where the train is stationary on the tracks and the situation where the train is moving with constant velocity. So let's just kind of jot down a couple notes here to drive that point home. Okay, so the laws of science are the same in every inertial reference frame. As long as you're moving at constant velocity, it doesn't matter what that velocity is, you'll always get the same result for any experiment you do. This comes from Newton. So this has been established for a long period of time when Einstein comes along. Then there's this guy called Maxwell, and he calculated something. Maxwell studied electric and magnetic fields, and he found out that light is really just a sort of interaction between electric and magnetic fields. And based on some math and what he knew about electric and magnetic fields, he calculated what the speed of light should be. So Maxwell calculated the speed of light. Turns out that actually the speed of light can change a little bit depending on what material it's in. Specifically, he calculated what it would be in vacuum. So in a region where there's no matter at all, if you suck all the air out of a room, turn it into a vacuum, Maxwell found the speed of light there. Now, this should sound a little odd because we've just finished saying that speed is relative. You know, I gave the example of that car going down the highway. One person saw the car as going 100, one person saw the car as going 20. Both of them were right. So how can we say the speed of light is a certain number? Shouldn't it depend on who's watching it? So this is odd. The number that Maxwell calculated was 3.00 times 10 to the 8 meters per second. And because we use this number so often, it's been given its own symbol, and we use the letter C. The speed of light, c, is 3 times 10 to the 8 meters per second. Or, if you want to get rid of the scientific notation, 300 million meters per second. So again, this seems weird. For normal objects, we can't just say they have a speed. I can't say cars go 100 kilometers an hour. Because even if I put a car, even if I have a car getting driven by a robot and I make sure it goes on cruise control at exactly 100, that's what it would go relative to the ground. But relative to some other car driving near it, it could be going a little bit faster, a little bit slower. A car can have a whole bunch of different velocities because I can watch it from a whole bunch of different places. So how can we just say the speed of light is this number? Shouldn't it depend where I watch it from? Well, it turns out it doesn't depend on that. And that's weird. The speed of light is the same in every inertial reference frame. Just like the laws of science were the same in every inertial reference frame, the same can be said for the speed of light. So to kind of illustrate this, I like to imagine a scenario where I have two people, one of them sort of on the attack and one of them running away. So let's draw this out. Here's one person. This person is on the attack. They have a rock, and they're going to throw it at this person over here. Who's running away. Not only do they have a rock, but they also have a laser gun. Okay, so let's say they start by throwing the rock. And let's say they can throw the rock at 30 meters per second. So the rock takes off towards this person who's running away. The rock is going 30 meters per second. And the person running away, let's say they're booking it. They're going pretty fast. They're going at 28 meters per second. A little unrealistic for a human, but bear with me. So 30 meters per second is pretty fast, but so is this runner over here. By the time the rock gets to them, how fast will they see the rock going? Well, it's going 30, but they're doing almost that. They're doing 28. So they'll see the rock pass them at 2 meters per second. 2 meters per second, it's probably fairly easy to dodge the rocks, so they're able to do that. But person number 1 here, the attacker, has another weapon as well. They fire their laser gun. Now, since the laser is light, it travels at the speed of light. 300 million meters per second. So what you might ask, or what I'm going to ask here, is how fast does the runner see the light go past them? Now, intuition would say, well, they're going to see it going at 300 million meters per second minus the 28 that they're doing themselves. But that's not how light behaves. Remember, if Maxwell was able to calculate the speed of light, that means it doesn't matter where we're watching the light from. Otherwise, it could have a bunch of different speeds. The speed of light is the same in every inertial reference frame. So since this guy is an inertial reference frame, they have constant velocity, and this person is an inertial reference frame, they have constant velocity, both of them see the speed of light as being the same. So my runner sees the light go past them at exactly 300 million meters per second, the exact same speed the original person sees, not a meter per second less. So that should feel weird, and that's okay. What I want to do now that we have sort of these two important facts, that the laws of science are the same for every inertial reference frame, and the speed of light is the same for every inertial reference frame, we're going to use these two facts and put ourselves in Einstein's shoes. And we're going to try and derive one of the first equations he came up with for his theory of special relativity. And we're going to do it by trying to solve this problem here. So, consider a train of height h moving at speed v. So, here I have a train. Its height is h, and it's moving at a speed v. A person inside the train, here's my person, puts a laser pointer on the ground or on the floor and shines it up at the ceiling where the light bounces off a mirror and then returns to the floor. Another person watches from the ground outside, so let's add that person in. How long does it take for the light to bounce off the ceiling and come back? All right, so first thing to think about is we've got two perspectives here. There's the perspective of the person inside the train, and there's the perspective of the person on the ground. The person inside the train is going to see the light go straight up above their head, hit the mirror, come straight back down, and land right by their foot, exactly where it started. But the person outside the train is going to see the light, start at the laser pointer, but as the light moves up, the train is moving to the right. So what I've done here is this is the exact same train, just drawn a little bit later in time. And here's the exact same train a little bit later. So as the train moves to the right, I've just drawn it a couple more times. Think of these as sort of 3 photographs that are taken of the train at different times. So the person on the outside actually sees the light go from the laser pointer up to the mirror, and then from the mirror back down to the laser pointer, landing there a little bit later. So while a person in the train just sees the light kind of go up and back down, the person outside the train sees the light kind of follow this triangular path like that. Okay. So let's start solving this problem by just sort of collecting the information we know about what both of these observers see. We have a little bit of information here about speed of the train. We have the height of the train, that's a distance. And we're being asked for how long it takes for something to happen. So that's a time. So sort of speed, distance, and time seem to be the 3 things that are relevant in this question. So let's write down what we know about those things. And because there are 2 perspectives here, 2 people watching this happen, I'm going to write down what we know from both of those perspectives. So on this side, I'm going to write down what the person in the train sees. And on the other side, I'm going to write down what the person on the ground sees. So the person on the train watches the light bounce off the mirror and come back, and they see that it has a certain speed. They see it covers a certain distance, and they observe it to take a certain amount of time. Similarly, for the person watching from the ground, they'll see the light as having a certain speed. They'll see it as covering a certain distance. And they'll see it as taking a certain amount of time. So what are these numbers going to be? Well, the distance is maybe the most straightforward one. The person in the train sees the light go from the bottom of the train to the top. So that's h. And then they see it go back down to where it started. So that's a total distance of 2h. How about the distance that the person the person on the ground sees? Well, that's this sort of funky triangle shape here. That's going to be a little harder to figure out, but let's see if we can. I'm going to start by turning this into an actual triangle. So if I make a right angle triangle like that, I'm going to try and figure out what the lengths of this triangle are. So this here is the height of the car, h. And this length, this is basically how far the train travels in half of the time it takes the light to go up and come back down. So time is going to become important here. Let's say the person on the ground measures a time. We're just going to call it delta t. That's how long the person on the ground says it takes for the light to go up and come back down, delta t. So that means since speed times time is distance, the total distance from here to here is the speed of the train times the time it takes, or v delta t. So that means then that just this first leg of the journey, that first half, is going to be v delta t divided by 2. Okay, so I know this leg has a length of v delta t over 2. This leg has a length of h. I want to know what this is. Well, to do that, we're going to just use the Pythagorean theorem. So I know that this squared plus this squared, and then I take the square root, will give me that guy. So the length of this hypotenuse in my triangle is v delta t over 2 squared plus h squared. So that is going to go here for the distance the light travels. But since the light has to go not just up, but down again, I have to do that distance twice. So the total distance the person on the ground sees the light travel is 2 times that. Okay, so now let's talk about the speed here. Well, remember we were just saying on the previous page that all observers, as long as they're in inertial reference frames, see light as traveling at the same speed, and that is 300 million meters a second, or c. So the person on the train is going to see this laser moving at speed c, and the person on the ground is going to see this laser moving at speed c. That's true as long as they're in inertial reference frames. So as long as the train is moving with constant velocity and the person on the ground has constant velocity, that's going to be true. Now here's where it gets a little bit weird. Here I have an object moving at a certain speed and covering a certain distance. Here I have an object moving at the same speed, but covering a greater distance. If an object goes the same speed as another object, but covers a different distance, it has to take a different amount of time. Let's say you hop in your car and you drive at exactly 80 kilometers an hour till you get to the nearest town. And then another day you hop in your car and you drive at exactly 80 kilometers an hour, the same speed, but you drive 2 towns away, a greater distance. That second drive has to take you a different amount of time. If you're going the same speed, but a different distance, it's got to take a different amount of time. So what that means is that the time that the person on the train sees and the time that the person on the ground sees are going to be different. So I can't just call them both delta t. I need to have slightly different symbols for them. I'm going to call this one delta t r. And this r stands for rest frame. We say the person on the train is in the rest frame. And that is the frame or the perspective where the event starts and finishes in the same location. So the reason the person in the train is in the rest frame is this. If I ask this person, where did the laser beam start? They'd say, right down here, just beside my toe. And if I ask the same person, where did the laser beam end? They'd say, right here, just beside my toe. From their perspective, the start and the finish were at the exact same place, just beside their toe. So for that reason, we say they are in the rest frame. The experiment, the thing we're timing, isn't really moving relative to them. It starts and finishes right beside them. The other person, however, the observer on the ground, is not in the rest frame. They see the laser start way over here on the left, and then the train whizzes past them, and when the laser gets back down to the ground again, the train's way over here on the right. They see it as starting and finishing in 2 very different places, so they are not in the rest frame. Now I want to just take a moment here to write down something key that we mentioned before, and that's to highlight the idea that these 2 times are different. So we said that because the 2 observers see the light traveling at different distances, but with the same speed, they will measure different times. And we call those times delta TR for the person in the rest frame and delta T for the other person. Okay. Now I want to continue our math. Another fact I've used here, we said before that the laws of science were the same in every inertial reference frame. And that is why I'm allowed to sort of do this next step here, which is say, since we've been looking at speed and distance and time, we should think about a law of science that kind of has to do with those things. And turns out there is one. There's a formula that relates those things, and it looks like this. Speed is distance divided by time. And since the laws of science are the same in every inertial reference frame, if that applies for the person in the train, it applies for the person on the ground too. Both of them, this formula applies for the worlds that both of those people are in. Speed is distance divided by time. So let's take the things we have and plug them into this formula. The person on the train sees the light moving at speed c. The distance they see the light moving is 2h, and the time they see it takes for the light to go up and back down is delta tr. For the person on the ground, the speed is c. The distance is this guy, and the time is that. Okay, so because the speed of light is the same for every inertial reference frame, we said that both of these watchers saw the laser moving at speed c. And because the laws of science are the same in every inertial frame, we said that both of them could say speed is distance divided by time. And that got us these two formulas here. Now, it is a little bit annoying having to always do everything twice here. Whatever I do on the left side of this table, I have to do on the right side of the table. Whatever I do for the person in the train, I'm doing for the person on the ground. It would be great if we could sort of combine the information from both sides. And that's what I'm going to try and do here with a little bit of math. And what I'm going to do is I'm going to take this formula on the left-hand side here, and I'm going to rearrange it for h. I'm going to isolate h. And if I do that, I get h equals c times delta tr over 2. Next thing I'm going to do is I'm going to take this new expression that I have for h, and I'm going to substitute it in over here. That will help me combine this equation with this equation into one equation, and I'll no longer have to do everything twice. I'll just have one formula, one equal sign, that kind of has all of this information tied into it at once. And I'm going to write that equation for starters on my next page here. And here's where instead of writing H, I'm going to write this stuff. Okay, so there I've taken this equation over here, combined it with this equation here to get this equation down here. So from now on, I no longer need to do things on the left and on the right. I've got all the information combined into one equation. Now, because this equation is asking me to find how long it takes for the light, that means I basically want to try and find delta t. And it always sucks when the thing you're trying to find is in the bottom of the denominator. So let's try and move this up to the other side. Let's multiply both sides by delta t. And that will give me okay. Next up, I'm thinking that this square root is going to be annoying. So I'm going to get rid of that by squaring both sides. It's always nice to get rid of a square root sign if you can. So we're going to square both sides. And actually, I'm just realizing what might be a little simpler is if let's go back a second. Because it's delta t that I'm trying to find, it would kind of be nice if this was sort of by itself. So I'm going to take this c and remove it. Move it to the other side. I'll divide both sides by c. Then I'll do the squaring both sides that I was talking about. So let's divide by c. And now, let's try and get rid of that square root by squaring both sides. Note when I square the right-hand side, I'm going to have to square everything. So this 2 gets squared to become 4. This square root gets squared, meaning it goes away. And this c down here gets squared to become c squared. Okay, next thing I want to kind of deal with here is all these brackets. These brackets in here only really exist because I want everything inside them to be squared. And same on this side. So I could get rid of those brackets if I simply just took the square and applied it to everything inside. You could call this distributing the exponent. So let's do that. So notice what I've done here. Everything inside here got squared. So the v became v squared, the delta t became delta t squared, and the 2 became 4. Same over here. C becomes c squared, delta tr becomes delta tr squared, and 2 becomes 4. That's allowed me to get rid of one set of brackets, which is nice. The next thing I want to do here is I want to clean this up further. I want to get rid of these brackets, and I want to get rid of this fraction. So the only reason I need these brackets is to remind me that everything inside them is getting multiplied by 4. So I can just take the 4, distribute it into the brackets, and I won't need them. Similarly with this fraction, everything on the numerator needs to get divided by c squared. So if I just do that, divide everything by c squared, I don't need that fraction. So that's what we're going to do next. Distribute the 4 and the c squared. So you can see my 4 from outside has now come in, and my c squared from down on the bottom has now come up to here. And the same on this side. Now is my favorite step. I get to cancel some stuff out. You can see that over here I have 2 4s, one on the top and one on the bottom, so they can cancel out. I have the same thing over again in this second term. And also in the second term, I have a c squared on the top and the bottom that can both cancel out. That's going to simplify things a fair bit. So here's what I'm left with now. Okay. Next up, let's remind ourselves that the thing we want to find is the time. Got a delta t over here and a delta t over here. It'd be great if they were in the same place, right? Combine like terms, you could say. So let's take this whole term over here, and move it to the other side. So those delta t's are together. Next up, now my delta t's are together, but I still have two of them. It would be nice to just have delta t written once, so I have a chance of getting to an equation that just says delta t equals. And I can do that by realizing since both of these terms have a delta t, it is a common factor, and I can factor it out. In fact, it's not just the delta t I can factor out, it's the delta t squared. And it's this last step that I find sometimes loses students. Going from here to here isn't obvious. And what I would maybe advise people to do is look at the step in reverse. So if I take this delta t and I expand it by distributing it into here, multiplying it by the 1, multiplying it by this v squared over c squared, I would get back to this thing up here. And hopefully that convinces you that everything I did in this step was all right. So the last thing I'm going to do now is isolate this delta t, get it on one side all by itself by moving this stuff back over here, and then getting rid of this squared by square rooting both sides. And so note here, when I square rooted, sorry, not squaring both sides, square root both sides. When I did that, delta t squared became delta t. Delta tr squared became regular delta tr. And this stuff on the bottom all got square rooted. So this final equation here is what's known as Einstein's formula for time dilation. We kind of reasoned way back up here that when we were measuring this event, the time for the laser to go up to the ceiling and come back down, these two people, the person in the train and the person on the ground, would measure different times. That's why we assigned them different symbols. And what we've just done is we've come up with an equation that tells us just how different those times are. If this is the time measured in the rest frame by the person on the train, then I can plug a number in there and solve for this, the time measured by the observer on the ground. So there's Einstein's formula for time dilation. Now, there was a lot here. And honestly, I don't expect most people to finish this with like a good big picture idea of what we just did. And most of the time along the way, I don't expect you to be able to, understand necessarily why I'm doing each step that I'm doing. But here's what I hope you take away from this lesson. I hope you take away that the laws of science are the same for every inertial reference frame. Doesn't matter whether I'm moving or not. If I do an experiment, I'll get the same result. I also would love it if you took away from this lesson that the speed of light is the same in every inertial reference frame. Then, taking those ideas, we kind of went through the same process Einstein went through, came up with this thought experiment about this train. And we said, okay, if the laws of science are the same in every inertial reference frame, then both of these people can say speed is distance divided by time. And if the speed of light is the same in every inertial reference frame, both of them will see the light at moving speed c. And then here's where I think the genius of Einstein comes in, is a lot of people just looked at this and said, that's bizarre. Like, there's no way that two people can measure the same event and get different times. But Einstein just kind of said, well, what if they did? Let's just stick with it and see what the math would say about it. And look at the math that we did. Here's what we did. We did some algebra. We moved some stuff around to isolate something. We substituted one thing in for another thing. This is sort of like grade 9 math, grade 10 math at this point. We multiplied both sides by something. We divided both sides by something. We squared both sides. This is simple algebra. We took an exponent outside some brackets. We put it into some brackets. Some more distributing. We did some canceling. That was great. We moved things from one side of the equation to the other. This is probably the most complicated math we did. We pulled out a common factor. And then early on, we used Pythagoras to find one of these distances that light traveled. But that's about it for the math we did. It's not that complicated. People have this sense that Einstein was this crazy math genius. And when it comes to some of his other theories, yeah, math was important. And there's some complicated math that goes into this. But for his theory of special relativity, it's not the math that is surprising here. It's Einstein's ability to just take what other people thought of as bizarre and impossible and just stick with it and see where it got him. If you look at the physics we did, it's even simpler. There's one physics formula, one physics idea we use in this whole thing, and its speed is distance divided by time. So with some really simple physics and some pretty simple math, that even if you weren't able to see where I was going with it, you were hopefully able to follow every step. We can come up with Einstein's formula for time dilation, which I think is is a pretty incredible thing and something to be kind of proud of. If you were able to follow along every step to this, that's pretty neat.